So now we'll have Laura Starkston from UC Davis, and she will talk about singular symplectic isotopy problems.
Okay, so I want to first say thank you to the organizers. This is the first time I've been to Brazil, and it's fantastic. So I'm very glad to have some friends here in Rio. The math I want to talk about today, I want to start by just discussing a kind of classical subject, which is in the complex projective plane. If we're working in homogeneous coordinates, x, y, z, each complex numbers, we can look at a complex curve, which is just the zero set of a polynomial. So, I don't know, maybe something like x squared y plus y cubed minus 3 z squared x plus 5 x cubed is 0. So we want it to be homogeneous so that it's well defined in these coordinates, and that describes some complex curve, and I'm going to call it degree 3 because it's a degree 3 polynomial. So if I vary the coefficients that I have in front of my different degree 3 monomials, there's also some zeros in here, then I get different curves, and I can see what does the family of all degree D curves look like, in this case degree 3 curves. So if I want to connect one degree 3 polynomial to another, I can connect them through degree 3 polynomials by just changing the coefficients from these ones, 1, 1, minus 3, 5, and a bunch of zeros, to whatever coefficients I want. Now, if I pick certain particular coefficients, then the curve that's described by this polynomial can have singularities. So sometimes this is singular. So what kind of singularities can we have? Well, in this degree, we could have something like maybe x cubed minus y squared z equals 0. This one has a singularity at xy equals 0. And the singularity looks, in the kind of real picture, it looks like a cusp. But if we're working with complex numbers, this cusp is really a little trefoil knot. That's a trefoil, that's shrinking down to a point. So if you just take a family of trefoils, shrink them down to a point, that's giving you a picture for what's going on at the point 0, 0, 1 here. So that's some kind of singularity that can occur. Another kind of singularity that could occur is maybe this polynomial factors. So maybe it's something like, I don't know, z y squared minus z x squared equals 0. So this has factorization into 3 linear factors. And so each of those linear factors is like a line. But a line in CP2 is really a sphere. So there's kind of these 3 spheres. Each pair of them intersects at a point. So we have 3 intersection points. Some other phenomenon we could have is maybe the 3 linear factors are all intersecting at the same point instead of intersecting at 3 different points. So maybe we have something like x, y, x plus y equals 0. And then you have this other kind of singularity with 3 branches coming in. OK, so these are sometimes singular, but for generic coefficients, they're smooth. So the curve is smooth. And so if it's a complex curve that's smooth, it's a real surface, and it has some genus, and the genus is determined by the degree. So the genus is d minus 1, d minus 2 over 2. This is just the adjunction formula applied to CP2. And so this holds both for complex curves and for almost complex curves like symplectic curves. So what I want to talk about today is not really complex curves, but symplectic surfaces in CP2. And complex curves just give us a kind of nice model set of examples of symplectic surfaces. Or I'll call them symplectic curves because the curve surface thing gets very confusing. So I'm going to try and call everything curves so we don't forget and think that I'm talking about complex surfaces. But OK, just ask if you're confused. So in this degree 3 case, the genus of these guys is going to be a torus, genus 1. And as I get higher and higher degrees, the genus is getting higher and higher. So if I'm looking at the space of complex curves of degree 3, this is a finite dimensional space. The dimensions are parameterized by the coefficients of the different monomials of degree 3. If I'm looking at symplectic curves of a fixed degree, this forms an infinite dimensional space. I could start with a complex curve, which is an example of a symplectic curve, and near any point on that curve, I could just perturb it a little bit, and as long as I don't change the tangent spaces too much, then it will still remain a symplectic submanifold. So this is an infinite dimensional space. So it's a little bit harder to understand than the complex curves. Yeah? Good question. So degree meant something for polynomials. So here, I want to mean it specifies the homology class. So the second homology of CP2 is isomorphic to the integers. So degree d, let's call this curve sigma, means that sigma represents d times the generator in second homology. So obviously, if two curves are not homologous, then they're not isotopic. But if they are homologous, then I could ask, are they isotopic to each other as smooth surfaces, as symplectic surfaces, as complex curves? So for smooth complex curves, if I start with two complex curves of the same degree and they're both smooth, I can get a family between them, connecting them, which are all smooth complex curves. And the reason is essentially I can find a family of generic coefficients connecting my coefficients for the one to the coefficients to the other. So the singularities occur with positive complex codimension, which means that I can always kind of go around them. There's no walls. But in the symplectic case, that same kind of question is actually open in general. So the symplectic isotopy problem is asking, what's the classification of symplectic surfaces in CP2? So if maybe sigma and sigma prime are symplectic surfaces of the same degree, are they isotopic through symplectic surfaces? So here we're talking about smooth surfaces for now. But you could also ask the same question for singular surfaces. So this is smooth version. And then the singular version, you could ask if sigma and sigma prime are symplectic singular and their singularities are modeled off of complex curves, so with same type of complex curve singularities, then we can ask, can we connect one to the other, keeping the same type of singularities throughout the whole family? And the terminology to shorten that sentence is, we can ask, are they equisingularly isotopic? So equisingular, same singularities, isotopic, symplectically. So the singular version is kind of more general than the smooth version. So what do we know in any of these cases? So if we're in the smooth case, Gromov, in his pseudo-holomorphic curve paper, answered this question in low degrees for degrees 1 and 2. So if the degree is 1 or 2, then the answer is yes. Any two symplectic surfaces of degrees 1 or 2, if they're both the same degree, will be connected to each other through symplectic surfaces of that same smooth degree. And then the techniques were extended to degrees 3, then 4 and 5, and then up through 17 by Shevchishin, then Sokurov, and then Siebert and Tian. And then they kind of ran out of steam. So what happens is that as you get to higher and higher degrees, all of these guys are working with pseudo-holomorphic curves, and they're looking at a family of pseudo-holomorphic curves that are trying to represent these symplectic surfaces. And if you're in degree 17 or higher than 17, your genus is pretty big. And when you get to larger and larger genus pseudo-holomorphic curves, then the theory gets more and more complicated of what kinds of degenerations can occur and how to try to rule out those degenerations. So the smooth theory gets hard because of high genus. I think they seem to say somewhere that like you could do the 18 case. It's just every time you do another case, you have to work out more like case analysis. So they could probably push to 18 if they wanted to, but then it would be a lot of work to get to 18, and then you'd have to do a lot of work to keep going. So I think it's kind of like at a certain point, until you can get the general thing, you get bored of doing one case at a time. So what I want to do is kind of go in a different direction and go in the singular direction. And the advantage is that for singular curves, you can get to arbitrarily high degree without having high genus. So the singularities can kind of eat up the genus. So in these cases, you can kind of see it even in degree 3. The smooth degree 3 curve is a torus, has genus 1. But then if we kind of degenerate it down to lines, each of the lines is a sphere. So we've got 3 spheres intersecting with nodes. And if we degenerate it down with this cusp, then the sort of underlying geometric genus of the object is genus 0. So the genus 1 got kind of eaten up into this trefoil cusp. So I'm going to use that to stick to low genus, but get to arbitrarily high degree. Any other questions?
So for these singularities and the singular curves, are you like allowing these kind of non-generic singularities, like the same way?
Yeah. Right. So I'm going to take like the singularities that occur for non-generic coefficients in complex curves and use that as a model. Yeah. So these are the same types of singularities that can occur for pseudo-holomorphic curves. So if you sort of want your symplectic surfaces to be able to be represented by a pseudo-holomorphic curve, like there exists a J such that they're pseudo-holomorphic, then you should restrict to singularities with complex models. So this is joint work with Marco Gola. So we're going to, look at singularities modeled on complex curves. So in general, you have different options for what these singularities can look like, but the link of the singularity, so that means what do you see as your knot or link shrinking down to a point as you zoom in towards the singularity, that's going to be an algebraic knot or link. In these cases where the curve kind of breaks up into components, we have sort of multiple branches coming in at the singularity. So I'm going to restrict so that instead of having multiple branches, I just have a single branch in my singularities. So we'll fix on locally irreducible singularities. So that's what we're calling cuspidal. And in this case, the knot that you see here, this is a trefoil for the degree 3 case. In general, it could be a torus knot, or you could take a torus knot and do an iterating cabling operation. And so we're going to look at the kind of first level case, which is just torus knots. So we'll only have cones on torus knots, TPQ. So you can think of your model as looking like x to the p equals y to the q. So at the origin, there's a singular point, and your knot is wrapping p circles in one direction and q times in the other circle direction. Okay, so given these kinds of singularities, the other restriction we're going to do is low genus. So we're going to look at the lowest possible genus you could have, which is genus 0. So rational will refer to genus 0. P and Q are coprime, yes, because I want a knot, not a link. Okay, so let me state some results. So the first families that we can look at to go with this lowest genus 0, but get to arbitrarily high degree, is with just a single cusp eating up all of the genus that comes from the degree. So if we look at rational, so genus 0, unicuspidal. So this means one singularity. symplectic curves. Let's say we have sigma and sigma prime, both rational with a single cusp, and the cusp is the same type. Cone on a particular torus knot. Then, if they're living in CP2, they are symplectically isotopic. So sigma and sigma prime are symplectically equisingularly isotopic. So there's only one isotopy class of these curves in CP2. So there are two infinite families of these that occur. If you have a p plus 1 torus knot, you can find degree, I think, p curves which have all of their genus eaten up by this one torus knot. And then there's another family, which is p for p minus 1, I think degree 2p, where you kind of just eat up all the genus into a single singularity. So this is what these curves look like in CP2. There's a unique isotopy class of them. You could also ask, could these kinds of singular surfaces occur in other manifolds, other closed symplectic manifolds? And the techniques that we use to show that they're unique isotopy classes in CP2 basically give a classification of all the closed symplectic manifolds they could live in. So CP2 contains some curves with these types of singularities, and S2 times S2 contains some of them as well. And then there's a few kind of sporadic cases that can live in some blowups of CP2. For certain values of k. So in general, these have unique isotopy classes in CP2. In other manifolds, they also typically have unique isotopy classes, except for one particular curve has two different isotopy classes in CP2 blown up 6 times. Two isoclasses. So there's a little bit of different phenomena that can occur, but these isotopy classes are distinguished by homological methods. Yeah?
So if I start with a smooth curve of certain genus, can I deform it to one of these guys?
That's a good question. So if you start with a smooth curve, if you had a smooth curve of, say, high degree, and you could deform it to one of these guys, I think you could use that to show that it's symplectically isotopic to a smooth curve. So I did that when you deform to line arrangement, but I think these guys should be similar. So because these guys have a unique isotopy class, the only ones that could be deformable to them are ones that are kind of deformable to complex curves, because these ones can undeform to complex curves. So the question of whether you could deform it is going to kind of relate back to the smooth isotopy problem. And I think that if you wanted to kind of ask it independently of the smooth isotopy problem, you could try and find a family of Lagrangian disks with boundary on that curve, and that would tell you how to deform it down to this kind of configuration. And the way that those disks intersect on the boundary would kind of determine what singularity that you're getting.
But so any one of these ones, even though they are symplectic
Yeah. Okay, so I didn't say this in the statement. So they're symplectically equisingularly isotopic to each other and to a complex curve. Yeah, so there's kind of two pieces of information here. One is if the singularity type doesn't admit a representation by a complex curve, then it doesn't admit a representation by a symplectic curve either. So there's a kind of abstraction level, and then there's the isotopy level. So if there's a complex curve, then there's a symplectic curve also. But could there be symplectic curves which are not isotopic to the complex curve? And the answer here is no, because they're all isotopic to each other. Yeah?
Are there any examples in which you can compare topologies of these two spaces? Say you have something about how the space of complex curves sits inside the space.
Yeah, so that's kind of interesting. I think there are a lot of really interesting questions. So you've got your complex curves being some space. Maybe it's complicated, maybe it's disconnected. And then you've got this kind of massive infinite dimensional symplectic space. And all we're saying here is that the symplectic space is connected. So does the symplectic space have some non-trivial pi1? That's a great question. And then relative to the complex space, even at the level of pi0, it could be theoretically, although in these cases, the algebraic geometers are interested in this question of if you have, you specify your singularities, are your singular curves like diffeotopic to each other? And this says the answer is yes, they're diffeotopic to each other in this case. So they would be called Zariski pairs if they weren't diffeotopic. So there's no Zariski pairs with this type. And it's not clear in the literature that they knew this, but maybe you can put together a bunch of results and maybe they knew that. But the moduli spaces of complex curves can be disconnected even if they represent kind of the same diffeomorphism class of curves. So what we're finding is, just what's the pi0 of the symplectic world? And I think it's sort of very interesting to ask, is that bridging two disconnected complex moduli spaces? Could the opposite happen? Could you have a kind of connected complex moduli space and then two disconnected pieces of symplectic curves? So that's ruled out here. Basically, everything about the topology of these spaces is interesting, and this is like the very first question you can ask is connectedness. So the first kind of level of simplicity you can ask for these curves is that there's a single singularity. The second kind of simplicity you can ask is you can let there be a bunch of different singularities, but put some bounds on the degree. So we wanted some examples where you can have lots of different singularities. And so maybe I'll just kind of write over this same theorem. If you get rid of unicuspidal symplectic curves, but add that the degree is at most 5, then again, we have the same result, that in CP2, when they exist, there's a unique symplectic isotopy class, and they only exist if the complex curve with the corresponding singularities exists. So there's a existence and uniqueness aspect to it. So let me give you a little bit of an idea of how these classifications work. So there are a couple of tools that go into trying to classify these things. One kind of goes back to Gromov with pseudo-homomorphic curves. So you kind of use pseudo-homomorphic curves for a lot of different things, but maybe I'll give you just a sketch of how Gromov used it to classify degree 1 symplectic curves, and then that will generalize a little bit. So the key ingredients are, first of all, every symplectic surface is a J-holomorphic curve for some J. So for some compatible, almost complex structure. So I have an infinite dimensional space of symplectic surfaces, but for each of those symplectic surfaces, I can find an almost complex structure which makes it J-holomorphic. And once I've picked a J, the space of J-holomorphic curves is a finite dimensional space. I mean, it may have some problems, but the nicest part of it is finite dimensional. But the space of almost complex structures is infinite dimensional. So that's how the symplectic surfaces get to be an infinite dimensional space. So the space of compatible almost complex structures is infinite dimensional, but it's contractible. So in particular, it's connected. So if I have two different J's, I can connect them by a family of J's, and I can try and look at T holomorphic curves for as I vary my almost complex structure. And then I can study the moduli space of J holomorphic curves if I specify the homology class. So what Gromov did is studied that moduli space together with an evaluation map, and for degree 1 curves, they're basically determined by asking that they pass through two particular points. So if I specify my J, fixing J, there's a unique degree 1 curve through every pair of points in CP2. So as soon as I pick my J, I pick 2 points, I've got my degree 1 curve. So if I have two symplectic degree 1 curves, one over here and another over here, then maybe I pick my 2 points here, P1, Q1, and this guy is J1 holomorphic, and here I have P0, Q0, and this is J0 holomorphic. So I'll maybe first go from J0 to J1, looking at curves through these 2 points, P0 and Q0. So maybe this is a J1 holomorphic curve, and then I can just move my points, P0 to P1 and Q0 to Q1, and I look at the curve through those points connecting in between. So then this one goes to this one, and basically nothing bad can happen in the middle because degree 1 J holomorphic curves are always smooth. They can't develop any degeneracies. So using this fact that there's a unique J holomorphic curve through every 2 points, not only can I do this for degree 1 curves, but I can do it for a collection of degree 1 curves. So if I had maybe 3 different lines, or 4 different lines, maybe they intersect in some non-generic way, then I can kind of emulate this procedure, and I can control some 2 points on each line. And if I have 2 collections of these sorts of curves, maybe I have one like this, and one picture of CP2, and then another like this, then I can kind of carry this one to this one by moving the j's and moving the points around. So these are a particular kind of singular curve where I've broken it down into degree 1 components. So if I can understand a configuration, I can sort of add on a line. As long as I only have to control at most 2 points on that line, then I can sort of work on classifying these guys up to isotopy using purely pseudo-holomorphic curve techniques. So that gives me a kind of base collection of things where I understand their symplectic isotopy. But these guys are kind of different from the sorts of singular curves that I'm interested in here, because these guys, I haven't broken them into multiple pieces. I just have a kind of single component where I've eaten all the singularities into one of these torus knot singularities. So the second tool is to transform the types of singular curves that I'm interested in into curves that I can say something about. And the way to transform them is through blow-ups and blow-downs, so birational transformations. So I want to just draw a picture of the first case of these. So of sort of both situations, the very first non-trivial case is when I'm looking at a cusp of type T23, the trefoil that I started out with, a degree 3 curve. So I'm kind of, this is the first case in both of these situations. So let me do an example of the degree 3 curve with one T23 cusp. So I want to classify these guys up to isotopy. So this was actually done in this particular case previously by Ota and Ono, but through a somewhat different technique. And what I'll show you right now is going to generalize to the first infinite family of these guys with a single singularity. So I'll show you it in this case. OK, so we start. I'll just do it all on this board. So this is representing our degree 3 curve. Here's the cusp. And because it's degree 3, its self-intersection number is 9, which is 3 squared. And just because I can, I'm also going to keep track of a line which is tangent to this curve at the singularity. So by line, I mean a symplectic line or a J-holomorphic line. So it intersects this curve only once tangentially at the singularity. And then I'm going to do some birational transformations, which means I'm going to start blowing up. So when I blow up at the singularity, the nice thing about blowing up is that it makes singularities go away in a different way than just changing the coefficients did. So changing the coefficients would kind of smooth out the singularity, but you get the genus back. If you blow up, you get rid of the singularity, but you still keep your low genus. The cost is that instead of being in CP2, when you blow up, we've gone into a different manifold. So we're in CP2 blown up once. So the curve, if you started with this simple cusp coning on the trefoil, it becomes smooth. And then we have a new exceptional sphere, which is tangent to the curve. So the fact that it's tangent means if I blow it back down, I get back to the singular situation. And then I have this line that was tangent going through here. And then I can just blow up again. So my now smooth curve stays smooth, but I'm going to kind of start separating out these things. So the thing that was tangent now intersects transversely. This is my new exceptional sphere. And the thing that it intersected transversely is now disjoint. And then if I blow up again, always at the same point, then I'll separate out these two intersections. So new exceptional sphere. This guy becomes -3 from -2. This guy is -2, and it's got this orange -1 hanging off of it. And then we'll just keep going. Why not? So we could blow up again. The +3 goes on to a +2. We get another new exceptional sphere. And then all the rest of this stuff kind of moves off a little bit. So this -1 becomes a -2. It's got this guy hanging off of it, this guy, and this guy. And then we'll just do it one more time. Maybe you're starting to see the pattern now of what these blow-ups look like. -1, -2, -2, -3, -2. Okay, let me make sure I didn't make any mistakes. I don't have any 4-manifold people in the audience. Should be okay. So now I've blown up a bunch of times. I got to CP2, blown up once, twice, 3 times, 4 times, 5 times. The thing I've gained is I went from having my cuspidal curve of degree 3, self-intersection 3 squared, which was 9, and now it's become this nice, smooth +1 sphere, which would be a line if I were just in CP2. But I'm not in CP2, I'm in CP2 blown up 5 times. So now I'm going to start blowing back down. So I'll take this guy and start blowing down. But instead of blowing down in the way that I blew up, I'm going to blow down a different exceptional sphere. So this orange -1 guy is a perfectly good exceptional sphere that I can blow down. So if I do that, then the orange guy goes away, and the -2 becomes a -1. Then I can blow down this new -1 sphere. And then I've got another -1 sphere, so I can keep blowing down. So if I blow this one down, the -3 becomes a -2. This becomes a -1, -1, +1. Then I'm going to blow down this newest -1 sphere. And then I've got one more -1, so I'll blow that down. And I'm left with this configuration. So I'd blown up 5 times, and now I've blown down to CP2 blown up 4 times, 3 times, 2 times, 1 time, and 0 times. So I'm back to CP2. So every time I did these blow-ups, I included the exceptional sphere. So the neighborhood of this guy has the same boundary as the neighborhood of this guy, and that has the same boundary as the neighborhood of this guy. I'm just kind of doing these blow-ups on the interior. And then when I blow down, all of the things I'm blowing down are exceptional spheres in this picture. So what I get at the end is, if I want to understand this cuspidal cubic together with this tangent line, then that's equivalent to understanding these 2 lines in CP2. So this birational transformation gave me a way to equate the symplectic isotopy problem of two lines to the symplectic isotopy problem of these complicated curves. And this one I can solve with Gromov, basically. So there's a unique symplectic isotopy class of two lines. And so if I want to find an isotopy of these kind of curve like this in one picture, and another similar curve in another picture, then I can, in both pictures, blow them all up and then blow them all down and turn them into lines and do the isotopy of the lines. And the family of the lines that connect them will blow up and then blow back down to give me a family of curves connecting these guys. So I kind of translate my difficult problem into an easier problem. So you could ask, like, where did this family of blow-ups and blow-downs come from? This was kind of an arbitrary sequence of diagrams. So particularly throwing in this tangent line here was a little bit arbitrary at the beginning. So what's secretly going on is that the real kind of thought process behind this picture is what we care about is this white curve, which is singular. The first goal of blowing up should be to make this curve not singular, to make it smooth. So that was accomplished at the first step. The second goal is to make it look like a line. And a line has self-intersection number +1. So we just keep blowing up more and more times until it becomes self-intersection number +1. And then somehow I knew that I wanted to have this orange guy to blow down. So what happened at this point was when I do this for the first time, I don't have this orange line. I blow up and I get the red and white curves. And I say, OK, what homology classes should these represent in CP2 blown up 5 times if this one represents a line? And so you go through the homology calculation, and the homology calculation says, well, it would be really nice if there was an exceptional sphere. Like the homology tells me there should be some exceptional sphere that intersects only this guy and none of the rest of the guys at the homology level. And so then I say, well, if I had a curve like this, where would it show up in here? And that's where that line comes from. So this kind of transformation is a way of taking a curve with some kind of singularities and turning it into a collection of curves which are simpler. Yeah?
Are the birational transformations for torus knots well understood? Is that why it works so well for...
Yeah, so basically the number of times that you have to blow up to smooth something can be determined by which knot you have. And torus knots are, simpler. So I guess what I want to do, if I'm doing a trefoil, so I draw my torus knot as a braid, and then the effect of a blow up on the braid is I sort of do this blow up, and then I get to undo one full twist. So these guys get undone. So there's one full twist on those 2 strands. And then if I kind of ignore this red component, this is just an unknot. I could untwist it. So the fact that it's an unknot, it means, well, the unknot is the link of a smooth point. So if I had a higher level torus knot, then I'd have to maybe do a sequence of different blow-ups in order to kind of break it down until it gets to an unknot. But there's a kind of recursive sequence, which allows you to determine how this goes. And that tells you how the exceptional spheres will intersect as you go along. So there's kind of a homological game and a knot theory game that you play, and then you figure out what can I simplify this to. Good. So maybe one thing that's interesting about this kind of game is that, so in this case, we played it with a curve that exists in CP2, and we equated this problem to a problem where there's a unique symplectic isotopy class. So we use the unique symplectic isotopy class here to show that this guy has a unique symplectic isotopy class. But you can also play this game in order to show that things don't even exist in CP2. So you can play this game on curves where the moduli space is empty by doing a sequence of blow-ups and blow-downs. So I'll just show you one example. So there's a degree 5 example. So if I was degree 5 and I were smooth, my genus should be 5 minus 1, 5 minus 2 over 2. So 2 times 3 is 6. So I should eat up 6 genus in cusps. So one way to eat up 6 genus is to have a 3-5 cusp, and then 2 trefoil cusps, 2, 2, 3 cusps. So the trefoil ate up genus 1, and the general formula for how much genus PQ torus knot eats is P minus 1, Q minus 1 over 2. So this eats this much genus. So this is 4. And then each of these eat 2 minus 1, 3 minus 1 over 2, which is 1 genus. So we've eaten 4 plus 1 plus 1, which is 6 genus. So we've eaten up all the genus, so the rest of it is rational. It's genus 0. So this is theoretically a curve that satisfies the adjunction formula that could exist. And for some algebraic geometry reasons, in fact, there's no complex curve like this. But then you could ask, is there a symplectic curve with these kinds of singularities? Symplectic is a lot more flexible than complex curves. You don't have to be described by a polynomial. Like, why shouldn't we be able to construct something like this? So in fact, if you do a sequence of blow-ups, so you could blow this up, and again, you blow it up until it becomes a +1 curve, and then it's got some exceptional guys. In some configuration, which doesn't really matter what it is. And then you can say, well, if this existed in a blow-up of CP2, then there would be some other exceptional spheres that I could blow down. And that's invoking some pseudo-homomorphic curve results on existence of exceptional curves. And what this would blow down to is a configuration in CP2 of 7 lines intersecting at 7 triple points. So there's a birational transformation which starts with this curve and then implies that this configuration exists in CP2. So if this exists in CP2, then this exists in CP2. And what this is 7 lines with 7 triple points. So this is referred to as the Fano configuration. It's the set of points and lines over a field with 2 elements. But this doesn't exist over the complex numbers as a collection of lines, and this doesn't even exist topologically. So this does not exist in CP2, even topologically, even smoothly. So that's something I proved a little while ago with Danny Ruberman. So these kinds of complicated curves can't exist because they can be translated into configurations of lines which can't exist. So we kind of take something which has complicated singularities, simplify the singularities, and then reduce it to a problem which we can understand. So this is the abstraction side of things. It could have been that there was a curve which existed in the symplectic world that didn't exist in the complex world, but in this rational cuspidal case of degree 5, that's not the case. So we can find abstractions. There's one case where that doesn't really happen. It's not quite cuspidal. So there is a degree 8 curve where the singularities are not locally irreducible. I don't know, draw something. But each of the singularities looks like a cone on a 3-5 torus knot together with a smooth branch intersecting it transversely. So this is a type of singular curve which exists symplectically, but there's no complex curve. And I think that there's a unique isotopy class of these guys symplectically, but there's a little bit of details that needs to be figured out for that. So there's a lot of different phenomena occurring, and as you get to more and more complicated singularities and higher degrees, you can find different phenomena, and I think there's a lot of open problems to think about. So this is just sort of the first stages and some tools to address the problems. All right, so I'll end there.